Okay, great. So looks like I am audible to everybody. So let me begin. So the agenda today is going to be pretty small. What I'm going to do is I am going to quickly take you through the slide deck, which will take probably around 30 minutes or so. And once we are done with this slide, we will take questions from you, and we will try to figure out that how we can most effectively resolve your issues or help you out with your queries. So, and please feel free to interrupt me in between any time and ask whatever questions you have. Okay, so to begin with, the agenda today is going to be, first of all, to understand what exactly is secure web gateway. Then to understand the points of bottleneck in various scenarios for secure web gateway. Some protocol math, which we are going to talk about, that okay, how the protocol work and how the scaling and the bottlenecks work in the background. So that we are going to try and understand. And finally, we are going to talk about what SafeSquid can do for you. So this is going to be the 4 key agenda we are going to talk about. So it's going to be a pretty short and slick presentation, hopefully. I hope to get as many questions as possible because I would like to make this as interactive as we can. Okay, so of course we will have question answer at the end as well. So to start with, when we talk about proxy servers, the traditional approach is something like this. If you can see on the screen, this is how a standard proxy server deployment will be happening. And this is nothing new. This has been happening since probably last 2 decades. And we have been seeing proxy servers in enterprises everywhere. Proxy servers have been helping us to connect and share our internet connection across the network. So nothing actually new. If you see here what is happening, so I'll just try to get the pen out. Okay. So a standard network is in place. If you can see, this is a standard network. Then we have a switch on the network. This can be various switches in the networks, multiple switches, cascaded and all. They all terminate to a standard proxy server, which then finally passes through the data to the internet. Absolutely straightforward, no configuration, no confusion, straight stuff. This has been happening since ages, so nothing new. Now what is happening nowadays? This has been happening since probably about 20 years. So what has changed in the recent times? In the recent times, the internet gateway has no more an independent entity. So now internet gateway is being used for multiple tasks. It is not just passing the internet connection from the network to outside, or it is not just for sharing the internet connection, but we are using it for multiple things. Things like we are using it to integrate the proxy server with authentication servers so that we can make sure that whoever is accessing our internet connection is legitimate, and at the same time we can also track who is accessing what. So this has become a very, very crucial component which integrates very closely with a internet gateway or a proxy server for that matter. When we talk about authentication servers, they can be of various types and forms. So for instance, we can have an inbuilt authentication server inside the gateway itself, which doesn't talk outside but has its own user database and allows the users to access the internet based on that. Or we could have a centralized company-wide single sign-on capable authentication server like probably LDAP or KDC or Windows ADS for that matter. So there are various types of authentication servers which are deployed in a standard organization today. And a proxy server today should be capable enough to talk to any of these authentication servers and allow the users accordingly. And at the same time, help the logging system to make sure that all the authentication requests are coming in, all the users are tracked properly, and we can also make sure that who is accessing what. So this is one of the most critical component which is getting integrated with proxy servers nowadays. Okay. The next is of course the antivirus engine. So it has become a liability for any organization to make sure that the data which is going out or for that matter coming in is clean. So anybody or any organization will not want that its domain or its internet connection is actually propagating or sending out viruses. So to make sure that this kind of a thing doesn't happen, we integrate our gateway with an antivirus engine which scans the outgoing data flow and tells you that whether the data is clean or not. and if it is not clean, it should be capable enough to block it as well. Now this antivirus engine, pretty much like the authentication server, can be of various forms and factors. So for instance, it could be incorporated inside the proxy server application or hardware. At the same time, it could be a separate entity by itself. So pretty much like authentication server, another very integral component of internet gateway nowadays. Reporting engine. Okay, so this is also very important, because when we start doing authentication, the agenda is not just to make sure that the guys who are accessing the internet are just able to access it if they are allowed to. But at the same time, the admin also should be able to know that who is doing what. How is the productivity going, which kind of sites they are accessing, what kind of downloads they are doing, what kind of mails they are sending. This all should be logged up to a certain extent, so that the enterprise network or admin is satisfied enough to know that okay, the entire crew in the organization is using the internet for productive purposes. So this is also a very integral component. Again, like the other two, this also could be integrated inside the same proxy server, or could be a separate entity which can be clubbed with the proxy server. But the essence here is all these components has to work with the proxy server some way or the other, so that they keep sharing the data with each other and give you a consolidated reporting at the end of the day. Okay, so the standard new approach looks something like this, if you can see on the screen right now. So what is happening is we still have the same network as before. If you see, the network is right here, the switch is right here in place, we have the proxy server, but now what is happening is we have a bunch of parallel components also sitting just beside the proxy servers. We have the authentication server in place, we have the reporting server in place, we have the antivirus engine in place. Now all these components are integrated in some way or the other with the proxy server and scanning the data which is going out through the proxy and which is coming in through the proxy as well. So this is what is a standard scenario we see nowadays in the industry. So if you see, I'm sorry, there's a problem with my mouse. So if you see, this is the new block which has been added with our proxy servers nowadays. So what has happened because of this? So if you just quickly go ahead to the next slide, we'll see what exactly is happening. So the new approach, if we select a standard UTM or hardware gateway like device to do this kind of tasks, what we are essentially doing is we are putting everything under one single chassis. So because the number of components which are relying on the proxy server has increased, and at the same time we are using a hardware device and we are trying to club all those components to the same box, what exactly is happening is we are putting everything under one single chassis. Now what is the problem with that? This makes the device very resource hungry. Now be this standard hardware box or be this customized desktop or a server machine with your own implementation of UTM application or whatever. The moment we start adding more components to it, like the user authentication database, like the reporting system, like the antivirus engines and all, it becomes more and more resource hungry in nature. Okay, so that further needs more and more resources inside one single box. So what's happening is nowadays if you go out and try to see hardware gateways or UTM devices in the industry, you will find that they are mammoth. They have multi-quad core processors, they have some 1632 GB of RAM, they have 4 hard drives plugged into it and all. Now why is that necessary? Because we are not just using that small little box, or not exactly a small little box for that matter, that huge box for doing your connection handling, but we are also using for doing a lot of things. We are using it for scanning viruses, we are using it for reporting, we are using it for authentication, we are using it for so many things. And when we specifically talk about UTMs, we are also loading this particular box with other applications like anti-spam, like mail servers, like things like that, like a regular stateful firewall. So it even becomes more and more heavier in nature. So that's what is the scenario which we see nowadays. Now this not only makes it very expensive single point of failure, but it also restricts us from scaling up and down individual components. Now the entire presentation today which I am going to take, I'm going to just focus on these two parameters and these two facts, that how are this becoming a pain for the enterprises nowadays. So what is happening basically is, because we are whenever we are using a single hardware box and we try to go ahead and scale it. Now why would you like to scale it? There are two reasons. One could be simply because we are losing out in terms of number of connectivity, a number of connections. So we need more resources, and this single box cannot have more hardware plugged into it. So what we do is we get another box, plug it in parallelly, start distributing the connections and make the network slightly more scalable. That is one reason of scaling. The other reason of scaling is fail-safe. Now, if we are putting everything in the same box, if we are putting all the eggs in the same basket, then we would of course like to make sure that we have a fail-safe mechanism implemented somewhere. So the moment we say that we need a fail-safe mechanism deployed, we are actually talking about buying the same box once again. So what is happening is, probably we don't need to scale each and every component of that hardware box, and we just need to scale one particular piece of it. But because the entire thing comes in a single package, whenever we have to go ahead and whenever we have to scale it, or we have to make a fail-safe deployment, we have to buy the entire thing once again. So what is that doing? That basically makes sure that basically lets you increase the amount you invest on this kind of boxes at the multiple of the unit price. So what is happening is, if let's say I am buying a single hardware for X amount, the moment I talk about scaling it, I have to pay 2x. Similarly, I have to provision 2x of my rack space. I have to provision 2x for my data center real estate in terms of electricity, in terms of cooling and everything. So it is actually increasing at the multiple of 2 the moment we are trying to add a single unit to the system. So this is what is one of the major issue with a single box like hardware gateway or UTM deployment. Now, so what would be a standard approach if we go out and see today? So let's say some organization has decided that they will deploy UTM, which will take care of all their security needs. It will be acting as a firewall, it will be acting as a content filter, as a standard proxy server, as an authentication system and whatnot. So now what happens is, with a standard UTM based approach, you will be putting most of the components into one box, obviously, except probably the authentication server, which could be a secondary deployment in your network, which is basically an extension to your Active Directory or something like that. But most likely, and what I have been seeing in at least the SMBs around me, that people actually don't go ahead and even extend that bit to their UTMs. They actually use the inbuilt database of the UTM to do the authentication at the gateway level, which actually is not the right way, but that's what is happening. Larger enterprises still go ahead and do authentication using the authentication servers and integrate the UTM with that. But yeah, that's what is happening nowadays. So a standard UTM type deployment will look something like this. So what is happening is, all the components which I was talking about, the authentication system, the reporting system, the antivirus, anti-spam, everything clubs into a single component and gets inside this one tiny little box, and that takes care of all the outgoing data from your network to the internet. Correct? So this is what is happening as of today. If you see, just give me a minute. I think I have got a chat message somewhere. Okay, no, okay. All right. Okay, so back to the presentation. Okay, so this is a standard UTM approach which we see. Now, if you just go ahead. Now, scaling this UTM will essentially mean that you are going to deploy another exactly same device on the network. For fail-safe, you will be anyways doing that, because nobody in an organization is going to be using a single point of failure for everything. So basically, if somebody doesn't deploy a fail-safe mechanism for their UTM, what it means is either the entire connectivity of the enterprise to the internet goes down, or it just passes through unchecked. So the network is actually in a situation where it can be compromised, because the UTM is also your first level of firewall. So nobody will be deploying the UTM independently. They will at any point of time go ahead and implemented as also as a failsafe. So they will have two units sitting and doing the same task. A much wiser deployment would be most likely is to use the UTM in a load balancing manner, so that when both the devices are on, they are actually serving active, and if one goes off, the other takes the entire load. Probably the connection speed and the connection limit will be reduced, but at least the connection will be still live. So that will be a wiser approach. There will be people who will be saying that, okay, I am going to use a standard active passive deployment for UTM. So my secondary one is going to sit back and rest till the time the first one dies. And the moment the first one dies, the second one takes care of all the requests. So both are legitimate and both have its own benefits. But the problem is, in this kind of a scenario, what you are doing, you are basically buying two very expensive boxes for doing everything. And for failsafe, you anyways have to do it. Again, if down the line your number of connections start increasing, or if your requirement increase, then you might actually have to do the same activity for doing basic load balancing as well. So, and the moment you add one more, you are basically buying the same box one again. So making it from 2x to 3x to 4x to 5x, and it just goes on like that. So there is no other option. So if we just quickly go to the next slide, what we see here is a standard, very basic fail-safe and load balance deployment of a UTM in any organizational scenario. So what is happening is, we have our cascaded switches, we have the network. Then what is happening is the data is going to the load balancer. The load balancer is then pushing the data to one of the UTMs and doing round robin or whatever technique to distribute the data. The UTM is taking care of the data and pushing it out. This is going to be a standard deployment for any kind of a UTM setup or a hardware level gateway setup in today's age. So you see, this is basically the load balancer. I'm sorry, my mouse is acting weird. Just give me a second. Okay. Just give me a moment. Alright. Okay, so this is my load balancing device, which is accepting all the network connections from my switch and then distributing it to both the UTM devices. The distribution can be based on various algorithms. It could be standard round robin, where it just does the transaction on the basis of numbering, or it could be more intelligent and it could actually check for the resource utilization of one box, and based on that it decides that which one is the free device as of now and sets the data there. So that basically is going to be the capability of the load balancer, and it can be of various forms and factors, but at the end of the day, what is happening is the connection request is going to get distributed across through the UTMs and going to the internet. So this is going to be the standard scaling of UTM. Now the moment we say that we are again running out of resources on our setup, what we do is we probably add one more. My bad, 1 second, sorry. This mouse is painful. Yeah, sorry. Okay, so the moment we run out of our resources, what we do is we add one more box here and we just increase everything by from 2x to 3x. So the price of the UTM goes from 2x to 3x, the rack space requirement goes from 2x to 3x, and so on. So we are basically adding the same device again and again. Now what are we going to do to solve the problem? But before we go ahead and do that, let's also talk about one more very interesting aspect which we generally overlook. So the standard assumption is, if we are getting more requests, more connections, keep adding more processors and more RAM to the system, and that will help manage all the incoming connections and all the outgoing connections at the same time. But that actually doesn't work like this. There is a bit of a protocol level math which goes behind the scene and actually decides that how much you can actually scale a single hardware box. So if you actually go out and see a device which is probably running a 8-core processor with 64 GB of RAM and claiming to handle millions of transactions, concurrent transactions, it might actually not be the case, because there are other limiting factors as well. So we are going to just quickly touch base on which are those limiting factors. So these are some hidden factors which I am going to talk about right now. Okay, so when we talk about concurrent connections, there are many different pieces in play. Since a connection is defined by source and destination IP and source port and destination port, you are essentially allowed to have 65536 to the power 2 connections between two given peers at any point of time. And this is port to port. So technically speaking, this is actually a pretty huge number. So the 65535 to the power 2, and the same time that is port per port. So it is actually a pretty hefty number. But that is not always the bottleneck for us. There are other factors as well. So for instance, there's a small trick here. Every socket created for a connection, so what happens is, whenever there is a connection established between the proxy server to the outside world, it is actually consuming one particular socket. Now, these sockets have its own lifespan. So let's assume that a connection has been established. It is not necessary, or for that matter, it actually doesn't work like this, that the moment the connection is dead, the socket will also get released, because the socket has its own timeout or its own lifespan. This actually makes sure that if a connection dies, no other new connection can immediately start using the socket and breach the authentication. So this is actually used to safeguard the connection between two peers and make sure that there is no overlap happening between old and new sockets. But what it does, it basically reduces the practical number of possible concurrent sockets at any point of time. This is happening because the speed of new connections getting established is much higher than the speed by which my sockets are getting cleared or my sockets are getting vacated. So because of that reason, my practical number of possible connections after a certain period of time reduces much lesser. That causes a major bottleneck which we don't generally realize. We just go by the fact that 65535 to the power 2, huge number, fantastic, but that is not the case, because it's not going to work like this. Very interestingly, if you actually want to understand how the entire thing works, there is this small Perl script written by some hacker which actually blocks all your sockets by randomly opening all the sockets at a go. And because the socket timeout is higher than the pace by which this Perl script actually opens the sockets, what happens is it exhausts all the sockets at a particular IP and makes that IP dull, or for that matter, it makes the entire system stop talking to the network. You can actually go to this link if you want. I will share the deck. You can take the link from there as well. You can see there is a small, very nice little tool which will let you consume or exhaust all the sockets of a particular IP within a few minutes. And because of the lifespan of the socket, that machine will be out of the network for a decent amount of time. This basically proves the fact that the bottleneck on socket is actually achieved pretty easily. So just by adding more resources, you cannot help it. If your system is running with 8 cores or 16 cores or 64 GB of RAM, that doesn't matter, because at the TCP stack level, this is going to create a bottleneck for you. Now, how do we help it? So what I'm trying to say is the number is not unlimited and it can be actually breached very easily. But then again, there is a very interesting bypass. The bypass is you can use multiple IPs to bypass this, because this number is actually bound to a single IP address. So if, let's say, your device has multiple number of Ethernet cards, then you can actually start using multiple Ethernet cards with multiple IP addresses and keep increasing the socket limit by the multiple of the number of IPs you keep adding to the box. That is the very reason that the high-end hardware devices you see out there in the industry sold today has so many number of ports. It is not because of the reason that those machines will be actually talking to so many networks. That's why they have so many number of ports. These ports are actually given to make sure that tomorrow, if you are actually running out of your sockets, you can start enabling new IP addresses and start increasing the number of possible sockets for your system. Though people don't realize that, and they just keep thinking that, okay, those 14 nice looking ports in my hardware gateway is actually meant for adding 14 different networks or subnets. That's actually not the case. The case is this. But yeah, at the end of the day, you have to keep adding more IP addresses, doing the entire networking math to make sure that if you are running out of sockets, you are still able to manage it by adding more number of IP addresses. I'm sure this is a bit tricky to understand. So if in the end you have questions, please feel free to ask, or we can actually have a demo on this later on someday, and we'll try to demo how exactly the socket exhaustion works. Okay. So now that is not the only hidden factors we are going to talk about today. There are other hidden factors as well. So let's proceed with that. There are over and above the socket limitation, there are OS limitations as well. So most operating system limits the number of open file descriptors and handlers per user per process. So what basically happens is every user is allowed. I'm sorry, just give me a minute. I think I'm getting a chat message somewhere. Just give me a second. Okay, I'm sorry about that. All right, some user query. Anyways, so what I was saying is the file descriptors has a limit for every user. So what happens is any user running any process can only start a set number of files on a standard Linux deployment environment. This limit is used to be very low at some point of time, but now it has been enhanced. Right now it is somewhere around 1024 number of open files per process per user. So every process run by every user can only have 124 files at any point of time. This could be tuned, and most likely and hopefully whenever you go ahead and actually buy a hardware device for doing your UTM stuff, you should make sure that they are tuned to handle more number of files, because whenever you start to create a connection, these connections are nothing but a file in the Linux environment. So if it reaches that bottleneck, it will stop working. So 1024 is not a very heavy number. So what happens is, how the systems handle it is by running multiple number of processes, and every process, allowing every processes to reach the handler threshold. So that is one thing. Now there is another limitation in the picture. That limitation is basically system wide, and this is a pretty interesting one because this varies. Now this varies based on the Linux distribution you are at, based on the file system you are using, and this is a pretty decently heavy number, but this varies, and this can be again tuned, but you will not see the tuning happening in a standard hardware box. If I might just try to quickly go ahead and do a quick demo. If I can connect to a Linux server right now. I hope the screen is visible. Okay, so I'm just quickly connecting to a few Linux machines here. So I just go and connect to one of my production servers. Just give me a second. Okay, just got root. Now if I go ahead, I hope it is visible. If not, I'll just increase the font size a bit. Okay, I think it's too much. I'll just decrease it now a bit. Yeah, this looks fine. So I just quickly do a cat proc sys fs file max, and I hit the enter button. I see this number. This is around 1600. This is 160579. So it's actually not a very huge number, but this is basically the number which governs or restricts the number of files my system can have at any point of time. Now this is a global limitation. So be it any number of users or processes, this is the maximum number the system can achieve. So your machine, or rather for that matter this particular machine, cannot open more number of files than this. So this also is going to be a bottleneck for any standard hardware type gateway. Now if I try to connect to another machine, I'll just try to show you a very interesting phenomena here. If I connect to another machine, let's say this one, right, let's log into this. I just quickly copy paste the same command here, go to this. Now if you see, the number has changed. Now this basically this number or this number of files is basically configured or basically handled by various things. It depends on which file system you are using, it depends on which version of kernel you are using, it depends on the size of the machine and all. This is of course very much tunable. You can go ahead and control and modify your kernel settings to change this, but people don't realize that this is also a very important aspect, because the moment your number of connections increase or reaches somewhere near this point, your machine will reach a bottleneck immediately. So this is one of the very crucial things which I needed to talk about. Okay, so let's go ahead and see what all we have. So, and there is one more layer of limitation or bottleneck for that matter. That is basically, let's assume that I am using a firewall on the same box. Now, if it is a stateful firewall, every connection or every state will actually be using a single entry on the process. Now, that will also have a count, and a standard firewall like IP tables will also have a limit for it. I'm not very sure about the exact figure here because this also varies based on the version to version, but yeah, that is also one of the limiting factors. So what I'm trying to tell you is, it is not just the size of the machine which matters. There are so many fine-tuned components in the system which also plays a very significant role to actually scale a single machine. So, and if you are going ahead and buying a box which is closed, which is like a black box where you don't get the access to the core kernel or to the core operating system, you completely cannot optimize this configurations, and you have to rely on the vendor on whatever they have provided. Now, their configuration could be very adequate for a certain set of scenario, but it could be completely misfit for a different kind of a scenario. And because you are not getting a chance to go ahead, study it and modify it by yourself, you are restricted with whatever they are providing. Okay, so now so we talked about all this. So what we are trying to bring to the notice is, you just cannot bypass a bottleneck just by adding more and more resources under the hood of the chassis. At the same time, you have to load balance. Obviously, at some point you have to go ahead and leave upgrading a single box and start load balancing, which is also very important. And when you do, in a traditional setup, as we talked about in slide number 9 and 10, we have to keep adding new boxes. You keep adding more boxes of the same time and most often same price. This keeps the price of the data center real estate going up in the multiples of the unit, which I already talked about. But interestingly, you might be just needing to scale a part of the system. So there are basically two things. One is, it is not always necessary that you actually need to scale every component of the proxy system. At the same time, it is also not necessary that the scaling is required just because you have hit the threshold of the hardware. It could be a fine-tuning issue as well. Now, in SafeSquid, what we do is, we provide a complete 360-degree approach of scaling. Now let's see what exactly is this 360-degree approach all about. Now the truth of the matter is, in majority of the cases, we never need to scale each and every component every time in a decently sized network. What we need is, I think I got a chat message again, just give me a moment here. Okay. Alright. So back to this. So we have a complete 360-degree approach. So now the truth of the matter is, we just don't need to scale everything every time. What we need is scaling specific components and rightly redirecting the traffic to the correct resource with maximum sophistication. Now this is something which I am going to talk about in depth in my next slides. So let's see what exactly I mean by this. Now, in a standard scenario, we have seen how the entire thing works. But let's say with an application like SafeSquid, what we do is, we don't ask you to scale the entire bunch all the time, because we are not just providing everything under the same hood, but rather we are ready to integrate with anything and everything possible. Now, my proxy server can of course go ahead and scale and set after a load balancer, but at the same time, it also talks with variety of authentication servers with variety of reporting services, and with variety of antiviruses. Now what this means is my proxy server can talk with a LDAP server, can talk with a KDC, and even can talk with a PAM. And the most interesting part is it can also talk with all of them at the same time in a hierarchical manner. So when I was actually talking about redirecting the traffic in a very sophisticated manner, I was actually talking about this. Now what happens here is, let's assume that when a user tries to access the network, the first authentication query goes to a ADS server, Microsoft Active Directory Services server. If the server is not available, or if the user in the server is not available, based on the policy, the query now goes to a KDC. Again, if the user is not available in the KDC, or the KDC is not available for that matter, the request can go to even a PAM. So what is happening is, we are not just providing an option for you to scale the proxy servers, but we are also providing an option for you to scale and create fail-safe mechanisms for your authentication servers as well. So in a corporate-wide network, you can actually create policies to make sure that at what point of time, at what basis, at what trigger, which authentication server is actually called for the authentication of the user before it connects to the internet. So this can be talking with multiple ADs, multiple KDCs, multiple PAM at the same time with a hierarchical manner if you do a correct deployment of the policies. So this is a very interesting feature which we provide, and we believe that this is something which we only provide. Similarly, when we talk about handling logs and reporting, exactly the same thing happens. So you can use our system to talk to cloud-based reporting application services like, let's say, Sumo, or let's say Splunk for that matter, or you can have your own local deployment of let's say Sawmill or Lyre for that matter, and or for that matter you can have both the things running parallelly, and both the things capturing the log and creating reports for you. So you can create specialized report based on which does what best. So for instance, if your Sawmill gives you a particular type of report which you need, you can generate it with Sawmill. At the same time, you can use Splunk to generate a separate kind of report. And if one fails, you have the data in the other one as well. So now that's exactly what I am trying to emphasize upon, that we are also letting you do fail safes and do scalability on components which we don't own. So you can actually configure based on our policies, fail-safe mechanisms and scaling mechanisms on the components which it talks to, because the entire thing works on policies and you can define everything in a hierarchical manner based on the policies. Now this could be a very nice demo subject which we would love to do probably later sometime, but as of now I'm just going to touch base upon the things so that you are aware of what all is possible with SafeSquid. Similarly, going to the antivirus engine, so we have our own hard-coded antivirus engine deep inside the heart of SafeSquid, but we don't say that you always keep using it, unlike other providers probably. We say that, okay, if you believe that you have another antivirus engine which does a particular task fantastically, you use it. And you use it along with our existing antivirus engine. You can again define policies. So let's assume you think that the antivirus engine which you have in your network, which is not a part of the SafeSquid application, does a brilliant task of scanning, let's say, office documents. So what you do is you create a policy which says that whenever there is an office document coming as an attachment, pass it through the antivirus engine which I own in my network first, and then pass it through the SafeSquid, or just don't pass it through the SafeSquid antivirus at all. It just talks to the antivirus engine of mine and does the job. And if you believe that some other component is taken care by our antivirus engine well, then you pass the data through that. You can even differentiate based on things like size of the file. So let's say if the size of the file is 200 MB, you can pass it through a different antivirus engine altogether. And if it is less than 2 MB, then it passes through the inbuilt antivirus of SafeSquid, or vice versa. So it's completely customizable. Again, it gives you a very flexible layer of scalability in terms of antiviruses which we don't even own. So we can talk, we can let the system create policies and let you manage and handle the requests based on your created policies and requirements, and talk to various third-party entities which we don't have direct control upon as well. So this is one of the very key component which I wanted to bring upon. I just have one more slide left, and I think we just have 5 minutes to go. So here's a quick checklist on what exactly we do. So we pretty much understood what we are providing in this particular slide, but just to make sure that everything is top in your mind, this is a quick checklist. So we let you do policy-based heterogeneous authentication, server integration and failover, as we talked about in our last slide, like this. So this is our policy-based heterogeneous, I'm sorry about the mouse again, policy-based heterogeneous authentication server configuration. This we already talked about. The second component is do policy-based heterogeneous integration with antivirus engines, third-party and inbuilt, just to add upon. Do policy-based heterogeneous integration with reporting systems, and of course we let you scale the core proxy server as well. So it's not just that we are letting you create policies and create fail-safes for third-party applications. We are also letting you do standard scaling and fail-safe for the proxy unit as well. Now, what we have is a very small footprint, so you can actually get the entire application in 20 MB. You just put it and it starts working. Very easy to deploy, has a default configuration in place. You can just extract the zip file and start using it immediately. We run on all Windows and Linux flavors. So from XP onwards, we support all the OSs on Windows. At the same time, Linux version and distribution, you name it, and we support that distribution. We run on all Linux versions. If you are on the Linux distribution, we also support portable app functionality, which basically means that you don't have to install anything. All you have to do is to just take a copy of the folder, put it on a different machine, and it starts acting the same way as the first one. You might need to create certain symbolic links though, but that's all you have to do. No installations required. So if there is, let's say, a disaster, all you have to do is to make sure that the folder where you had the SafeSquid configuration and the binary, you take a regular backup of it, you take that, put it on a different machine, and you are just as good as before. Now the distribution could be tuned for your exact needs. Now this is what I have been emphasizing upon since beginning. Because this application runs on a standard Linux distribution, you can go ahead and we can help you go ahead tune the entire distribution according to your own needs. So talk about the number of file limit, or talk about the kernel limits, talk about the socket limit, or whatever. We are there to help you out to tune the operating system exactly the way you want it to tune it. And because it is a standard Linux box on which we run, if you know Linux pretty good, you can go ahead and do your own kernel optimization and file system level optimization by yourself as well. So that is possible with our application. With the customization support, so we provide you a customization support, so where we can modify the architecture and the application exactly the way your setup needs. So you come and tell us what exactly you need the deployment for. What is your user base like? What is your deployment scenario like? WAN links, number of concurrent connections, what kind of sites. We help you with our support team to customize the entire application inside out for your requirement. Probably this is something which we are the only one who are providing, and nobody else is providing in the industry as of now. So now with this, I think I can come to the end of the presentation. I hope there are questions, but I'll just stop the recording at the moment and take the questions offline. So just give me a moment. But before that, please note down my credentials and the email IDs where you can reach us for any queries and any questions or demos you have. If you, let's say, want to see a demo of the entire configurations which we just talked about and entire scenarios, please feel free to write to us on information@safesquid.net, and we will schedule a specific demo for you where we will show you how exactly this entire thing happens on a standard deployment case. With this, thanks a lot for being here. I really appreciate your time.